Hello all. Today we are going to discuss the third electron displacement effect, which is the mesomeric effect or resonance effect, and we are dealing its applications also. Let's see the definition first. It's the effect caused by the phenomenon of resonance in a molecule. Okay, resonance effect or mesomeric effect is the effect caused by the phenomenon of resonance in a molecule. As in the case of both inductive and electromeric effects, this one also can be divided into two, which is minus M effect and plus M effect, or minus R and plus R. The groups such as carbonyl group, nitro group, NO2 group, cyanide or carboxylic acid group, when they are connected to a multiple bond, they will tend to withdraw the electrons, withdraw the pi electrons, okay, from the adjacent carbon atoms. Okay, this is called electron withdrawing resonance effect. Okay, this is called electron withdrawing resonance effect, as in the case of electron minus I effect. Okay, we can correlate with this one with minus I effect. Okay, so this is called minus R or minus M effect. Okay, electron withdrawing. If some groups, they withdraw the electrons through the multiple bonds, through the conjugated chain. Okay, this is called minus M effect. And similarly, in the opposite case, the groups such as OH, OR, NHR, NH2, Cl, etc., they will release the electrons through resonance. Okay, such groups are called plus R or plus M effect. Such groups are having plus R or plus M effect, and this is otherwise known as electron releasing resonance effect. Okay, so some groups will withdraw the electrons through the multiple bonds, or some other groups, they will donate the electrons through the multiple bonds. Okay, so the groups could be plus M or minus M. And one more thing, the groups showing plus M effect, they are called activating substituents. Okay, the groups showing plus M effect are called activating substituents, which means that they are increasing the electron density in the benzene ring towards electrophilic substitution. Okay, electrophilic substitution is a topic which is in the same unit itself, and we'll be discussing in detail in the coming classes. But I'll give you an idea. It's a benzene ring. This is a benzene ring, and here is one hydrogen atom, and this hydrogen H plus is an electrophile, and this can be replaced by other electrophiles. So suppose some other electrophile is coming, this H can be replaced by the incoming electrophile. This is called the electrophilic substitution reaction. Okay, and here the point is that if we are attaching one plus M effect group, if you are attaching, for example, if you are attaching an OH group here or NH2 group here, the rate of this electrophilic substitution will be very much higher. Okay, hope you got the point. If I am attaching an a plus M effect group in the ring, in the benzene ring, it will increase the rate of electrophilic substitution reaction by activating the benzene ring or donating more electrons to the benzene ring. Okay, now suppose if I am connecting this one with a deactivate, for example, NO2 group. Okay, suppose I am connecting NO2 group to the benzene ring. Now, let the same electrophile comes and attacks. Okay, the probability of this reaction to take place will be very much lower, because the NO2 group or the minus M effect groups, they will deactivate the ring. Okay, they will deactivate the benzene ring towards electrophilic substitution. Don't worry about it now. We will be discussing it in a separate video later. Okay, now we just want to know the thing is that plus M effect groups are called activating groups or activating substituents, and whereas the minus M effect groups are called deactivating substituents. Okay, now this is an illustration of plus M effect of aniline. Okay, aniline, there is a lone pair on nitrogen. Okay, there is a lone pair on nitrogen, and this lone pair through resonance will go down to between this carbon and nitrogen bond, and as a result this double bond will shift towards this carbon atom. And what can be observed here is that the lone pair, since the lone pair is lost from the nitrogen, this nitrogen will have a positive charge, and a double bond is formed here. A new double bond is formed. Okay, a new bond is formed, and the negative charge stays here. Okay, this is the first resonance structure we can write. And in the second structure, this negative charge will become a bond between these two carbon atoms, and as a result this from here this bond will shift towards this carbon atom. And the condition here is nitrogen is having a positive charge. Here is a double bond, and this negative charge has converted into a bond here, and here is the negative charge now. And in the third resonance structure, the same thing will get repeated, and we'll be getting NH2 plus double bond. Here is a double bond. Here is the newly formed double bond with this one, and here is the negative charge. In the next structure, what can we expect? This will go down, this will go back, and you will get aniline again. Okay, this is the effect of, this is plus M effect. Here nitrogen is having a lone pair, so that is donated to the benzene ring. Okay, the electron is donated to the benzene ring. Aniline is having a plus M effect or plus R effect. In this example, we can see that this NO2 group is having a minus M effect. For that to happen, electron density has to be shifted from this benzene ring to NO2 group. Okay, let's see how that takes place. This is the structure of nitrobenzene, and here this bond will, since oxygen is a more electronegative atom, oxygen will have a tendency to be a negative, to occur as a negatively charged moiety. Okay, so this bond has shifted to this side, and this nitrogen has a loss of one electron, right? Okay, this nitrogen lost one bond now. So to compensate that one, the nitrogen will pull this electron, pull this bond towards itself. Okay, so as a result, here O minus, this double bond has become O minus. Here a double bond is formed. Okay, nitrogen has compensated for its loss. Now this carbon lost its electron. Okay, the adjacent carbon lost its electron. Okay, and for this carbon, it has to compensate for its loss. So what shall it do? It will just take up the next bond. Okay, electrons from the neighboring bond. As a result, here this carbon gets the complete, or its valency is completed now. But okay, I'll have to write it from the beginning. Here is a negative charge, here is a negative charge, here is a double bond. Here is the newly formed double bond, and as a consequence, this carbon atom gets a positive charge because it has the loss. It lost one electron. Okay, to compensate for the loss of this carbon, again there will be a shift of pi bond. Okay, to form, here is a double bond, here is a double bond, here is a positive charge. Now, in the next structure, what will happen is that this negative charge that will go back. Okay, and as a result, this double bond will go to this one, and in the last structure of nitrobenzene will look like this. Here is a double bond, here is a double bond, here is a newly formed double bond, and now see this nitrogen, here double bond is not there, but still nitrogen has positive charge, N plus O minus, and here it is double bond oxygen. Okay, so examine this one again. It's a minus M effect. Nitrobenzene shows minus M effect because it is withdrawing electrons from the benzene ring towards itself. As a result, the benzene ring is having a positive charge in its carbon atoms, on its alternate carbon atoms. in the example of aniline, the benzene ring was having negative charge. Abundance of negative charge was there, but here positive charge is being circulated in the benzene ring. So this is an example of minus M effect. NO2 group is one of the most strongest groups which exhibits minus M effect. Minus M effect. Okay, now let's see the applications. First one is a comparison of acidity of alcohol and phenol. Normally, inorganic acids are called as a true acid or normal acid. For example, HCl. Let's take the example of hydrogen chloride. We'll be calling it a hydrochloric acid when this hydrogen chloride gas is dissolved in water. In that case, that is in the state H plus and Cl minus. Okay. So, in the case of HCl, both H and Cl, they don't exist. They don't like to exist as a covalently bonded species. It likes to be existed as in the ionic form, which is the more stable form, as H plus and Cl minus. Okay. Okay. And this Cl minus is more stable. It's a more stable species than hydrogen chloride, than the Cl present in hydrogen chloride molecule. Okay. And we have to take that analogy to explain this acidity of alcohols and phenols. Okay. So, ഞാൻ പറഞ്ഞു വരുന്നത് എന്താണെന്ന് വെച്ചാൽ H plus കൊടുത്തതിന് ശേഷം ബാക്കിയുള്ള സ്പീഷീസ് മോർ സ്റ്റേബിൾ എപ്പോഴാവുന്നോ അതായിരിക്കും മോർ acidic. എന്താണെന്ന് വെച്ചാൽ for example, phenol is more acidic than alcohol because after donating H plus, alcohol is becoming alkoxide ion and phenol is forming phenoxide ion. Okay. After the donation of H plus, alcohol is converting into an alkoxide ion and phenol is converting to phenoxide ion. Okay. As in the case of this HCl example la pole, Cl more stable ആയിരിക്കുന്നത് Cl minus ആയിട്ടാണ്. Not as hydrogen, but the part of HCl molecule. അതേപോലെ phenol exists in a more stable form of phenoxide ion. Okay, phenol tends to or would likes to exist as phenoxide ion. എന്തുകൊണ്ടാണെന്ന് വെച്ചാൽ because this phenoxide ion is resonance stabilized. Okay, the phenoxide ion is resonance stabilized. അതുകൊണ്ട് phenol ആയിട്ട് ഇരിക്കുന്നതിനേക്കാൾ ഇഷ്ടം എന്താണ് to exist as phenoxide ion. Okay, and this negative charge on this phenol is dispersed. This negative charge, അങ്ങനെയാണ് നമ്മൾ stability പറയാ. Negative charge is dispersed into the benzene ring. Now let's see the example of alcohol. Here, the negative charge, instead of dispersing the negative charge, because of the plus I effect of this alkyl group, negative charge and the density is increased here. Okay, other unstable condition. Okay, in the case of alkoxide ion, negative charge is not dispersed and therefore that is less acidic. So, alcohol molecule tendency instead of giving its H plus ion and exist as alkoxide ion. So, this is the reason why phenol is more acidic than alcohol. I tell you once again, the phenoxide ion is resonance stabilized and that is more stable and therefore phenol is dissociated into phenoxide ion very much easily. Alkoxide ion is not so stable, therefore alcohol will not be dissociated into alkoxide ion to a very much great extent. That's why alcohol is less acidic and phenol is more acidic. Hope you understood. What is the effect of substituents? That's another application which is more acidic. Okay, I'm asking you, I have given you 3 compounds. One is paracresol and the other one is phenol and the third one is para-nitrophenol. Now you have to tell me which is more acidic. And the thing you have to note down is that wherever the bond strength between OH, okay, OH bond strength, if the OH bond strength is higher, acidity will be lower. Okay, or hope you understood. Okay, OH bond strength എവിടെയാണോ കുറവ് കൂടുതൽ അത് less acidic ആയിരിക്കും. OH ന്റെ bond strength എവിടെയാണോ കുറവ് that will be more acidic. OH നമുക്കറിയാം, this is the standard case. In the case of phenol, we know that there is some Okay, this standard ആണ്. Phenol നമ്മൾ standard ആയിട്ട് എടുത്തു. Now we have attached two groups. This group is having plus M effect. This, okay, CH3 is having plus effect. Okay, and this NO2 is having minus effect. CH3 is having positive effect and NO2 is having negative effect. Okay, and this plus I effect, just remember that. And this, in the case of this CH3, this will give some sort of its electron density towards the benzene ring. Okay, alkyl groups, they will give the electron density towards the benzene ring, and as a result this OH bond strength increases. Okay, this OH bond strength increases. OH bond strength increases, and here this NO2 group is electron withdrawing. So NO2 group, this will withdraw the electrons from all the bonds, and as a result here OH bond strength is decreasing. OH bond strength decreasing. So we can understand that wherever bond strength, OH bond strength increases, acidity decreases. So the actual order is this one. Since NO2 group is a very good electron withdrawing group, that will pull the electrons from all over the molecule, and as a result OH bond strength decreases and acidity increases. Okay, and when it comes to basicity, the concept is the same, but you have to understand it in a different way. I'll explain. Here there is a lone pair with 2 electrons. There is a lone pair on all these 3 nitrogen atoms. Now when it comes to basicity, a base becomes a very good base when it donates its electron density easily. Okay, ആരാണ് ഒരു നല്ല ബേസ് എന്ന് പറയുന്നത്? അതിന് ഡെൻസിറ്റി ഏറ്റവും പെട്ടെന്ന്, ഏറ്റവും എളുപ്പത്തിൽ, ഏറ്റവും നന്നായിട്ട് ഇലക്ട്രോൺ ഡെൻസിറ്റി കൊടുക്കുന്ന ആളാണ് ആര്? ഒരു നല്ല ബേസ് എന്ന് പറയാം, ഒരു സ്ട്രോങ് ബേസ് എന്ന് പറയാം. ഓക്കെ, ദാറ്റ് വിൽ ഗിവ് അവേ ഇറ്റ്സ് ലോൺ പെയർ ഈസിലി. അപ്പോൾ ഇലക്ട്രോൺ ഡെൻസിറ്റി, ഇലക്ട്രോൺ അവൈലബിലിറ്റി കൂടണം. ലോൺ പെയറിൽ എവിടെയാണോ ഇലക്ട്രോൺ ഡെൻസിറ്റി കൂടുതലുള്ളത് അതാണ് നല്ല ബേസ് എന്ന് പറയാം. Okay, appo ipo nokka, ammonia is the standard. We have taken ammonia as the standard, and here in the case of methylamine, inductive effect nammal nokkana. Namukku when you explain the acidity, basicity and etc., you cannot stick on to just one effect and explain. We have to seek the help of the other points we have studied also. So here in the case of methylamine, this is more basic than ammonia. Okay, to explain that I have taken the help of the inductive effect. Okay, with this alkyl group is having plus I effect. Plus I effect ഉണ്ടാകുമ്പോൾ എന്ത് ചെയ്യും? Electron density is shifted away from the group. Okay, away from alkyl group electron density shift ചെയ്യും. അപ്പോൾ here electron density is increasing. Electron density കൂടുതലാണ് in the case of methylamine when compared to ammonia. In the case of ammonia, അവിടെ ഒരു effect ഇല്ല. Only 3 hydrogens are there, so there is no effect. Appo in the case of methylamine, since the methyl group is electron donating group, the electron density on the lone pair on nitrogen increases, is higher. Now let's see what happens with aniline. We have seen the resonance structures of aniline, and from there we have seen that out of the 5 resonance structures, among the 5 resonance structures, the 3 resonance structures will have the nitrogen with a positive charge. Okay, this is the first resonance structure, and that will continue to give you again 2 more structures with nitrogen having a positive charge. Appo nitrogen the lone pair കൊടുക്കുമ്പോഴാണ് അത് നല്ല ബേസ് ആവുക. അപ്പോൾ in the due to plus M effect of this NH2 group, എന്ത് ചെയ്യുന്നു? The lone pair is not present. ആർക്കെങ്കിലും കൊടുക്കാൻ വേണ്ടിയിട്ട് പോകുമ്പോൾ അവിടെ ലോൺ പെയർ ഉണ്ടാവണ്ടേ? നമ്മുടെ പ്ലസ് എന്ന് എഴുതുന്നത് എന്താണ്? ഇലക്ട്രോൺ ഡെൻസിറ്റി അവിടെ ഇല്ലാന്ന് കാണിക്കാനാണ് നമ്മൾ പ്ലസ് എന്ന് എഴുതാം. അപ്പോൾ ഡ്യൂ ടു പ്ലസ് എം ഇഫക്ട് എന്ത് ചെയ്യുന്നു? ലോൺ പെയർ ഓൺ നൈട്രജൻ ഹാസ് ബീൻ ഡിസ്പേഴ്സ്ഡ് ഇൻ ടു ദ ബെൻസീൻ റിംഗ്, സോ ദാറ്റ് ഇസ് നോട്ട് അവൈലബിൾ ഫോർ പ്രോട്ടോണേഷൻ. ഒരു പ്രോട്ടോൺ വന്നാൽ കൊടുക്കാൻ നൈട്രജനിലുള്ള അനിലിനുള്ള നൈട്രജന്റെ തലേന്റെ മുകളിൽ എന്തില്ല? ലോൺ പെയർ ഇല്ല. സോ ഇറ്റ് ഇസ് ദ വീക്ക് ബേസ്. It is a weak base. Okay, it's a weaker base than ammonia, and methylamine is a stronger base than ammonia. Okay. And now one more example of basicity, and we'll be winding up this discussions. Here, aniline we have taken as standard, and we have attached two groups, one methyl group and one NO2 group to aniline. And now we have to see what happens to the basicity. We know that there is a lone pair here. Most of the time it will be dispersed in the benzene ring, but still there is some amount of electron density over there. Now, suppose you are attaching an NO2 group. NO2 group in the speciality that is electron withdrawing, very much electron withdrawing. So that will withdraw the electron density through this pi bonds and all. Okay. And as a result, the electron density on nitrogen is decreased. When compared to aniline, the electron density on nitrogen is again decreased by the attachment of NO2 group. And in the case of methyl group, it is plus electron donating group, right? So electron donating group, it will shift some electron density towards this NH2 group. So here, electron density on nitrogen is increased when compared to these two structures. So a base becomes a strong base whenever it donates electron density. It has higher electron density to donate. Okay, the donating atom has higher electron density to donate. So this is a strong base. Para-toluidine is a stronger base than aniline, and which is in turn stronger than para-nitroaniline. Okay, so here in today's video we have seen the definition of resonance or mesomeric effect. Okay, and then we have seen that there are two groups, two types, which is plus R effect or plus M effect and minus R or minus M effect. And the groups which have plus M effect are called activating groups, and they increase the electron density in the benzene ring towards electrophilic substitution. And the groups which have minus M effect are called deactivating groups, which deactivate this benzene ring towards this reaction, or they are withdrawing all the electron density from benzene. Okay, and we have seen the applications of acidity of phenol and the acidity of amines. Okay, hope it is clear for you. Thanks for watching.